Okay, this is lecture G1, Building Physics, Design Principles for Facades. And it's going to tackle, yes, obviously, the design principles for facades. And we divided this in facade as an interface, the thermal insulation in winter and summer, humidity protection, acoustics, and daylight management, which are the aspects we deal with when we talk about facades. Facade interfaces. So this is an outline of influences of a facade, and obviously things like sun radiation, wind, ventilation, acoustics, noise are the aspects we have to deal with facades. And obviously the inside, the important part is the view to the outside. That's what we expect as an opportunity. That's what we're going to see in the glare protection later of this presentation. Outside, inside influences, solar radiation, external air temperature, ambient air, sound sources, acoustics, wind and rain versus illumination, glare, visual references, so the way the opportunity to see something, room temperature, surface temperature, inlet air temperature, air exchange, air quality, sound impact, air velocity, and mold and condensation are aspects the facade itself has to deal with as an interface. And we have to see the facade as a blocking interface. That's the simple part. And we have to see the facade as the interface which needs to have openings and allowing that there's an exchange between the one and the other side, the medium, which are to be used. And we continue with the first theme, thermal insulation in winter. Thermal insulation in winter. We call it the U value. U value is actually the sum of resistances of different materials versus the energy exchange. And we invert it to have the U value small, and small means better. No need to know this formula now by heart, just to understand, say, the general principle. And we see this with our facade. This is a single facade. This is outside, the other side is inside. Again, inside here, outside here. And we see that there's, say, the energy impact from outside, the energy impact from inside, and it either goes into the facade as we see it here, into the material as we see it here, or it is reduced by an insulation layer, which we see in here. This goes on with the same setup. This is an insulation at the inside of a facade, and this is an so-called cavity facade. We see an outer layer, we see a cavity here, then we see the insulation which absorbs a lot of energy, and then we see the inner structure which closes the system. Thermal insulation in summer works the same way, but vice versa. And here we have to deal with mainly thermal insulation in summer by the windows, so reflection of the sun, the absorption in the glass itself, some transmission, so the energy going through the facade, transformation, which means the sun light is transferred into heat and then radiates to the inside, and then the screen where we define which light goes through our system and which light needs to be reflected to the outside. Comparisons of different types of sun protection. This is then the way to secure that there's not too much sun getting into our system. No protection, horizontal shading, a brise soleil, as we say in architecture. So we see that horizontal shading, which blocks it off. We see an inner shading. We also can identify already that there's a lot of energy getting into the system and not blocked. And sun shading between the glass, which is happening in here. Actually a bit more efficient than this one because there's just one layer of glass where the sun penetrates, but then there's still an opportunity to get a lot of energy into the building. And then the outer sunscreen, which is technically speaking the most efficient one, which we will see in one of the later lectures. Humidity protection, we are aware of a house needs to be protected against humidity, water. We have all that water at the, say, basement of the building, which wants to find its way into our building, we need to make sure that the building at the outer part is protected against rain, which is driving rain, so horizontal flying rain, standard rain, and it's even this splashing rain, which means rain hitting a surface and then getting reflected. And in our DIN norms, we say 20 to 30 centimeter. That's the range of in which splashing rain hits our structure. Here again, we have to secure that our building is humidity protected at the outside. We either work with a quite seal protection, as we see here. So the outer layer, the plaster layer, protects the building. Humidity may get into the main structure, as we see it in here. If a single wall is given, it's the same. Humidity may get into the system and into the wall system, and also humidity maybe from outside next to, say, direct rain finds its way into the structure and then needs to dry out in dry times. Summertime, for example, needs to dry out of this wall system. If that doesn't work, then at a certain point the wall gets wet by time and then will lose its especially insulation performances. We can see the same with an inner insulation, where we hopefully have an entire sealed surface, and we can see this ventilated the cavity facade, which means there's an outer layer which is a rain protection. If there's any humidity in the system, it finds its way down here, and then there's the insulation which rarely takes humidity, and then the inner wall system which takes some humidity. But you see at the top drawing that say the humidity from outside is mainly blocked by this system. This is why they say technically are so well performing in this respect. Acoustics. Again, a huge formula. Frequency is the number of oscillations per second, so the numbers of oscillations per second. We have a certain human range of frequency which we can hear, but in acoustics we actually define a quite limited frequency which we technically use to deal with. And the main message is if there's an acoustic impact, it's an energy impact. And this energy impact is very limited by the energy which is confronting our structure. And the simple saying is the more heavier a structure is, the less this impact deals or appears being a problem. Which means that the solid strata structure in the means of acoustics works quite well. Low frequencies may be getting into trouble, but say mainly the structure being heavy helps a lot. The outer insulation, which we see here, and then the inner insulation, which we see here, we see that through the light structure, the acoustics finds its way into the solid structure. And here we see the cavity system. Again, acoustics finds its way through the light systems into the heavy systems, and then there is absorbed as a system. Again, this is calculated via a resistance, the R resistance, which is again a long formula which you don't need to dig into detail, which is a sum of the acoustic resistance of individual components being weighed by their size in the surface of the building. Daylight management as an aspect. Here we have this, say, conflict of functions. We need to protect, but we also need to supply. So protective functions means the glare shield, the sun protection to reduce the overheating, and the thermal insulation against heat losses to the outside, versus the functional, supply functions, which is our view, which we need to have at to the outside, which are solar gains in winter, which we really like to get, and it's the daylight input, which we need to have to reduce, need to go down, the energy saving against artificial light. So having too much sunscreen means that the daylight is reduced too much, and then we need to switch on the artificial light, which is energy-wise, not the most smartest solution. System switching, or the way we think about it, is the direct glare, which means the top part. We need to make sure that your person is not directly getting direct glare. It's reflected glare, which means reflection on a surface, and then the infield glare, which comes by the floor. And the position of the person already shows that this influences the glare. And you also understand that the higher the window sits in this system, the deeper the sun, the light gets into our room, which we actually at one point want to get more light in, and in other aspects don't want, because it delivers the glare as a risk. This is, say, north-oriented light. We see a lot of light coming in, but it's not giving direct glare as a system. And with this, I stop this small lecture about building physics design principles, so the main design principles which we use in building physics. Some literature if you're interested in this, and the last slide, the group of people which provided this lecture. And with this, I finish and thank.